All right, notes 8. We've already done a lot of notes, guys. All right, so real quick, guys, the first 6 here. I know that there's some calculators that have buttons, that have those buttons, cotangent, cotangent, secant, secant, cosecant, cosecant. No variety, I just went, okay, anyways. A lot of calculators don't, and that's because all of these are reciprocals, and you can get them by just doing the reciprocal of tan. Like, for example, number 1, it says cotangent 38. Well, that's equivalent to saying 1 divided by tan 38 degrees. So let's see what that is. I take my calculator, make sure it's in degree mode. It is currently not in degree mode. Mode, degree, enter. And now it's in degree mode. Your old ones, these yellow ones, don't have this bar on the top. But if you have a newer one, it does have that bar on the top. And now I'm just going to type 1 divided by tan with a 38. And there it is, 1.2799. Now, there is a button. I don't know how much of a shortcut it is. It's a reciprocal button. And tan 38, close it up and push this little button on the left-hand side next to the sine. That is not the same as arctan or inverse tan. That really does mean reciprocal. And sorry, guys, if this screen blacks out. We're pushing this laptop pretty hard because not only are we recording and we're using Dropboard PDF, I have a website in the background running. You'll see why in a little bit when we do the unit circle. So we're doing a lot of things with this laptop, so it might flinch in and out. It's just because it's running really hard. I can feel the heat coming off the laptop. That's how hard it's working. Anyways, so there it is. Make sure you know that that's called the reciprocal button. I kind of don't like it. I just like to push 1 divided by whatever. So do the rest really fast, guys. Cotangent of 140. That's 1 divided by tan of 140 degrees. So I'll just do it one more time, and then you guys will tell me the others. Negative 1.191, or that's truncated, 192 if it's rounded, right? All right. Secant of 238 is 1 divided by cosine of 238. So what is that number? Help me out, guys. Yeah, that one already have it. You can just type the button. What is it? Yeah, that sounds about right. Secant 53, that's 1 divided by cosine 53 degrees. I don't know what that number is. Cosecant's reciprocal of sine, so 1 divided by sine negative 179. Because this one's really close to negative 180, I expect this one to be big, like, I don't know, 40, 50, 60, maybe 70. So this one, number 5, is probably going to be a big number, negative big number. So hook me up with number 4 and number 5. What's number 4? This one's a positive number. Guys, 1.66. What? Give me 3 digits. 6661. 66661.
There we go.
Okay. What is number 5? This should be a negative big number. 40 or 50? 299. Okay. And number 6, without a calculator, can you tell me what this one is? Undefined. You can't divide by 0. So if you try to do it in the calculator, it'll give you an error. Cool? Okay. All right. I'm kind of excited and a little nervous about this. I have high hopes for this class. No. I have high hopes for all classes. Okay. Who has experience with waves? Sinusoidal waves, like math camp or something? No? Every day, right now, going through you you have some type of wave literally going through you. If you think about AM, FM signals that your car picks up, that's just the one giant wave. Well, the AM one is the giant wave. The FM is not. That's a big giant wave going through you. It's not very strong. Like, you don't feel it. Like, you don't feel the magnetic force. Like, it's not hurting you, but it's going through you. You got the sun rays hitting you. Right now, alpha and beta particles hitting you. Not very strong because we're kind of in the shade, but if we were to take a spectrum analyzer, you can probably see some of that. You got light waves hitting you, these light waves. You got the sound waves hitting you from my voice. It's going through your ear, and then it's bouncing up and down, and then going through your ear canal. So you got a whole bunch of waves hitting you guys. And hopefully, look, everyone here, or almost everyone, has a cell phone in their pocket. That's another wave. Your phone's constantly listening. So there's so many waves. You have so many waves going through you, so that's why they're doing all this research about, like, if you are constantly on the phone, like, is it creating, like, bad radiation for your brain and all that good stuff? Because it's literally, like, it's a signal, right? And it's literally going through you. And if you hold your cell phone to your face, like, you have that signal, like, hitting you right there. So they made I don't remember the article, guys. I don't remember the article. I wish I would have typed it out before we started today. They put a plant next to a Wi-Fi router. It's the same plant. They took a regular plant. I guess they call it placebo or regular plant. And then they took another plant, same type of plant, and they watered it the same. They did everything the same, but one of them was next to a Wi-Fi router. Guess which one grew faster and which one grew slower? The one next to the Wi-Fi grew slower, like statistically slower. So I don't know what's going on. I'm not sure if that means anything, but what I'm trying to tell you is maybe you should think about not having your Wi-Fi router like in your room. If it's like, yeah, so maybe put the Wi-Fi router away from, like, if you're having trouble sleeping or something, I don't know, maybe that signal hitting you all the time, blasting you, might not be so good. So maybe put it somewhere far away. You know what I mean? So think about that. Just think about it. Maybe putting it in the living room, right? Where, at night when you go to sleep, everyone's far away from it. Okay, so here you go. What's a wave? That's just stuff for you guys to think about. So here we go. I'm going to draw a wave, guys. It's not a perfect wave, but I tried to draw a wave. Right down the middle, try to draw right down the middle this green dashed line. That green dashed line it's called many things, but the two most common names is called midline. And in the scientific community, they call it the sinusoidal axis. Sinusoidal axis. So maybe if you take some science courses, they might call it sinusoidal axis. In math, they call it the midline. So depending on the university that you hit up, you might hear, those are the two most common names. It has other names. You can also call it your vertical shift in your vertical phase displacement and all that good stuff. All right. There's something called the max. So let me do that in blue. This is the max. I didn't draw it perfect.
It looks perfect.
Oh, thank you, miss. That's a min. Oh. All right, there we go. These points right on the midline, those are called points of inflection. Yes, you have. 100% you have. Those are called points of inflection. This is concave down. This is concave up. So point of inflection is where your sinusoid changes concavity. Or any graph, really, but specifically on the sinusoid. Let's see, what else? Period. It doesn't have to be peak to peak. It could be min to min. This is the period. It could be point of inflection going up to point of inflection going up. a period is made out of 4 quarter cycles. I guess I should put that in here. What color have I not used? Black. So here, from the max to the point of inflection, I'm trying to color code, that is 25% of a cycle. Oh, okay. I should also say this period is 1 cycle. That period is 1 cycle. What else do I need? Oh, frequency. Frequency is something you'll hear a lot in science. It's how fast a wave goes. And so frequency is just a reciprocal of period. What else am I missing? We got max, we got min, points of inflection, concave up, concave down, period, frequency, midline, 25% of a cycle. Anything else that I'm forgetting, guys? Okay. So we're finally getting into really good stuff for you engineers, especially the electrical and computer engineers. If you're a computer engineer, you're going to be dealing a lot with software and with signal analysis, so you're going to be doing a lot of this. If you're an electrical engineer, you're going to be doing a lot of programming and signal analysis, so you're going to be doing a lot of this. Yes. I'll pick it up in a little bit.
Yeah, my dad likes it, but he also likes that.
So do we have any experience with waves, like at all? A little bit?
My dad's software engineer, so he does this a lot.
Perfect. So then show him the notes.
Basically my father.
Yeah, show him the notes. So show him all this stuff. He's going to be like, yeah, that's what we do. All right, here's the question. I don't know if you guys will know because it depends on whether or not we have experience. But why have satellite dishes been getting smaller? They used to be huge, right? Like huge, like a decade ago. No, there's a relationship between frequency and wavelengths. Do you guys know it?
Oh, the smaller the wavelength, the more energy, the more radiation.
Oh, don't worry. I mean, I'm sure there's some truth to that. But I just want a relationship specifically between frequency and wavelengths.
The smaller the wavelength, the higher. The smaller the more compressed.
The smaller the wavelength, the higher the frequency. Yes. So that's why satellite dishes have been getting smaller and smaller because the frequencies have been getting faster and faster. Now, let's talk about something that does affect you guys, or it affects everyone. 5G. Your phones with 5G. Those wavelengths for 5G are really small. So if you get under a tree, your speeds are automatically reduced. No joke. Like you think your phone is fast with 5G, and it is. As soon as you get behind a wall, it's cut in half, probably even more. Get it under a tree, and because the wavelengths are small wavelengths, done. Like your speed, you're not going to have that speed. Go to YouTube and just put 5G speeds, and you'll see a whole bunch of people, like, they just go under a tree and it just cuts the speed. That's because the wavelengths are small. All right. 4G does not do that. I'm sure it's affected, but not as extreme as 5G. That's why they have to put so many. Well, let's not talk about. We're not in antennas course, so we don't know electromagnetics, so we can't, talk about all that good stuff. All right, so here we go, guys. A lot of this is review. Well, I don't know. It might be review. It should be review. On Thursday, we'll talk about transformations. Remember transformations of functions? If you are really good with transformations of functions, you'll be really good with this. So I have 2 sinusoids, and I just really...
Sinusoids?
Yeah, by the way, a sinusoid, just because it's the word sinusoid does not mean like, oh, sinusoid, he's talking about sine. Cosine and sine are both called sinusoids because they create this wave. Do we understand that, guys? So cosine and sine create this wave. The only difference is that cosine and sine are out of phase by 90 degrees. And you'll see what I'm talking about in a little bit. So check it out. So here it is. All this is just notes. A is the amplitude. It's the same thing for functions, right? B is the horizontal dilation. C is your horizontal shift. They also call it phase displacement. And D is your vertical translation or shift. Same thing with functions, guys. Same thing with functions. How do you compute well, here's the period, and then they tell you how you find your b, what kind of. This indirectly tells you how to get the b. The b is 360 divided by period. And we're working with degrees momentarily because you guys seem to like degrees better. So here we go. You guys ready? I'm going to do a sketch and emphasize quadrant 1 and 4 and make the high point 1 and the low point -1. And you guys are going to help me out here. Ready, guys? We just took a unit circle quiz. It's okay if we don't know it. 90 degrees. Let's start at 0. 0 degrees. What is sine of 0? All I'm doing is plotting. Y equals sine x.
Sine of 0
is 0. So put a point at 0, 0. I'm going to move a little bit, try to make them all symmetrical. I'm going to call that 90 degrees. Sine of 90 degrees. I'm going to go by 90 degrees. Sine of 90 is 1. Good. Someone studied. I'm going to go to 180. Sine of 180 is 0. Put a point at 180, 0. I'm going to go to 270. Sine of 270 is -1. And I'm going to go to 360 degrees. Sine of 360 is 0. Perfect. Where you have your maxes, try to put a bowl. And where you have your mins, put a bowl. Upside down bowl where max is like this. See? Bowl. And where you have mins, bowl. Try to make the points of inflection at the midline or the x-axis in this one. So it doesn't have to be perfect, but it looks pretty good though. And check it out, you got your first wave. Pretty cool, right? We created this just by the unit circle. And don't worry, in a little bit I'll give you an animation. Do the same thing for y equals cosine x. Let's draw a sketch.
Oh my god. Wow. All the previous values.
I'm trying to make it symmetric here, but okay. Here we go. For cosine, what is cosine of 0? 1. So at 0, put a point at 0, 1. Go to 90 degrees. What is cosine of 90 degrees? No, not 0. Put a point at 90 degrees, 0. Then go to 180. What is cosine 180? -1. Then go to 270. What is cosine 270? 0. And then finally go to 360. What is cosine 360? 1. At the maxes, put bowls, upside down bowls. At the mins, put upside down, put regular bowls. Try to make the point of inflection the midline. It doesn't have to be perfect. I feel like my sine graph was better, but that's fine. And look at that, we just sketched the parent function sine and cosine. Now I'm going to show you, check it out. I did not create this, I just Googled it and I went to Desmos. Someone created this here. I would like for us to get where we're doing explorations like this, but we don't have enough laptops. I guess we could use Chromebooks maybe, but that's fine. We first got to know what we're doing. So here we go. Ready, guys? Look at this. I'm going to click, and look, it's graphing the sine graph. That's cool, right? And it's just coming from the unit circle.
Oh my god, wow. I've definitely seen this before.
Don't worry, it'll come back on. And here's the cosine. See the cosine one.
Oh my god.
Cool or what? I think this is really cool. So now you know where sine and cosine come from. They just don't magically appear. Someone didn't just say, oh, I'm going to make a sinusoid, call it sine x, and another sinusoid, and I'm going to call it cosine x. No, guys, this was all discovered. It's part of the universe. Cool? Or not cool? Okay. So I'm going to close this so I don't use up so much RAM so there's less heat. I'm like sweating here because I can feel all the heat coming off of this thing. Leave. All right, so hopefully it won't work so hard. Okay, so here we go. Our first example. We're just going to sketch, and it doesn't have to be perfect, guys. All right, here we go. Suppose that a sinusoid has a period of 12 degrees per cycle. Do you guys like underlining stuff? So underline 12 degrees. And this is amplitude 7 units, so underline amplitude 7. And then phase displacement -4, so underline that. With respect to the parent cosine function, so cosine function. And a sinusoidal axis 5 units below the x-axis. Okay, they want me to sketch. So here, since I know that I'm below the x-axis, I'm gonna overemphasize quadrant 4. So here's how I'm gonna do it. Here's my grid. It's not perfect, but that's fine. I'm gonna draw my midline. I'm gonna say, let's see, sinusoidal axis 5 units below. So I'm gonna say this is 5 units below. I'm gonna say -5, ... You don't have to do the sound effects. And I know the amplitude is 7. So from -5, I'm going to go up 7. And I know that's the max. So -5 plus 7, I'm going to call that 2. And I'm going to go. So I know I'm not going to pass that. And then I'm going to go -5 minus 7. 5, 6, 7, 8, 9, 10, 11, 12. -12. Try to make it symmetric. So I'm going to say -12 is like right here. Okay, I'll stop with the sound effects. Sorry, guys. I've been doing that since college. Dr. Faltz would always make fun of me. I'm going to get him one day. Like, anyways. I'm going to email him. Dr. Faltz. Anyways, here we go. I'm going to be within the bounds of 2 and -12. Cool? I know they want me to do a parent cosine function. So let's observe where you are at for cosine. So this is my cosine graph. Everyone see this one? Yeah. Notice that I have a peak right at 0. So that's the point. This peak here is the point that I'm going to move 4 times to the left. Does that make sense? Because that's what they tell me, guys. Displacement -4 degrees. So I'm going to go -4. I'm going to say -4 is like right here. I'm going to put a point at -4, 2. And that's a degree. So put a degree there. So do that. Okay, I'll say it again. That's my point that I'm going to use. That's like my shift. Yeah. They told me that displacement is -4, and they told me to use cosine. You know what I mean, Abdul Karim? So I moved this max for the cosine. I just moved it 4 to the left. Because they told me my phase displacement. Phase displacement is your horizontal shift. Okay. Yeah, don't worry. You're going to be doing that all the time when you have an oscilloscope. You're going to be moving once you're an engineer. All right, here we go. What's the period? 12 degrees. So I'm going to go 12 degrees to the right. So -4 plus 12 is 8. I'm going to say 8 is like right here. Try to make it symmetrical. Try to make it like that's the distance from the origin 4. So that looks like 8 to me. And then put a point. You guys see? Yeah, see, do you guys see what I did there? And now, what's up?
Okay, why are you putting, before you put the numbers on the line, and now you're putting it on the maximum?
Oh, this is the x-axis.
Oh.
The black line is the x-axis. I'm not putting it in the midline, you know what I mean? Okay. I'm going to go every 12 degrees, I'm going to put another high point. So what's 8 degrees plus 12? So make it symmetrical. 20 degrees, put a point at the high. I'm going to go another 12. What's that, 32?
So it's still look like quadratic right now. They're running over.
No, don't worry. Well, okay. don't worry, miss. It's going to come out okay. I kind of feel like one more, guys. 20, 32, 42, 44. Point degrees. So I have 1, 2, 3, 4, 5 peaks. Are we still okay? Okay, now remember that I'm going back to just geometry. I'm knowing that from the max to the point of inflection, that's 25% of a cycle. So from the max to the min, that's 50%. Yes or no? Yes. So I'm going to go halfway just one time. Where do I want to do it? I guess between 8 and 20. I'm going to go halfway between 8 and 20, and I'm going to put a low point down here, the minimum. What's halfway between 8 and 20? 8, 9, 10, 11, 12, 13, 14. Yeah, 14. I'm going to label that one. And now I'm just going to add 12 every time, guys. 14 plus 12, 26, another point. 26 plus 12, 38, another point at the min. Do you see what we did? Okay, we're almost there. Look, we almost have a beautiful sketch. In between the max and the min, you have a point of inflection. I'm only going to label it one time. So in between the max and the min, I have a point of inflection right smack there. So 8, 9, 10, 11 at 11 degrees. And then 14, 15, 16, 17 at 17 degrees. Point of inflection. I'm just going to label those two. And I'm going to put a whole bunch, but I'm not going to put the degrees for the others. I'm just going to put it right in the middle. Right in the middle. Right in the middle. Right in the middle. And I didn't do this one, so let's see, negative 4, 8, 2. There we go. So now, what do we do? At the top ones, put bows. Try to aim the bow at your point of inflection. At the minimums, do the same thing. Put bows. Try to aim your bows to the point of inflection. Like this. If you want some examples, you can look up real quick before you do yours. See how I kind of have them aimed towards my point of inflections? And then I just connect them. They don't have to be perfect, guys, as long as they more or less look like that point of inflection does change concavity. And if it doesn't, that's fine, but just make it more or less. And wow, look at that. We have a pretty good graph. You guys just graphed your first sinusoid. What do you guys think? Pretty cool? I think this is pretty cool. You're winning. Everyone's winning. I wish we had pyrotechnics. Throw some fire. That would be real cool. Everyone would learn. Right? One of these days... Well, no, okay. Yeah. Here we go. Let's continue. In my head, I'm thinking how it would look, but... Alright, I'll stop. Find the equation for the graph you sketched. Okay, here we go. We use cosine, guys, so the very first thing I would do to help everyone, just write out the equation for cosine. A cosine, close, B, x minus c, close, close, plus d. We're literally just going down the alphabet. Did they tell me what the amplitude was? Yes. What was my amplitude? A, which was 7, the number, right? Did they tell me what my shift was? Yes, negative 4. So it's going to be a plus 4 when I write it in the equation. Do I know where my midline is? Negative 5. You can also say sinusoidal axis. So I got everything but B. But can I calculate B? Yeah. B equals, the period should have been 360. It's not. What's the period? 12. So 360 divided by 12 gives me 12 into 36, 12, 24, 36, 3. So 30. I got everything I need, guys. Y equals 7 cosine, open parenthesis, 30, open parenthesis again, x plus 4, put a little degree symbol, if you forget it, no big deal, plus, or actually minus 5. And there it is. And let's see if it works, guys. So don't worry, we're almost done. By the way, I don't want you guys to be robots. Do you remember, side note, real quick. Do you remember when you guys were in Algebra 1 or Algebra 2 and your teacher told you how does f of 2x compare to f of x? And what happened? What did that 2 do to your graph? Did it stretch it horizontally or did it shrink it? No, I compressed it. It compressed it horizontally. It compressed it horizontally by a factor of half, the reciprocal of 2. So
because it's the opposite of the vertical.
So that 30 comes from, your compression is 1 over 30. Check it out. 360 times 1 over 30 does give you 12 degrees. And look, 1 over 30, take the reciprocal, 30. So if you know like the principles, we'll talk about transformations on Thursday. All right, let's see real quick. Bless you. Y equals, what was the equation that we got, guys? 7 cosine 30 x plus 4, close, and then minus 5, right? Okay, let me check my window here. Window, I went from negative 5 to like 45 or something. 45, and then y min negative 15 to y max 5, and I don't care about that graph. So check it out. Here it is. I wanna check those coordinates, the exact ones that I was talking about. So I'm gonna put trace, and I already forgot. So which ones? At 8, I better have a max. At 11, I better be at the middle. At 14, I better be a min. 17, middle, and 20 max again. So help me out with those numbers there. So 8, trace 8, enter. Do I have a max at y equals 2 there? Okay, what was the other one? 11. So 11, enter. Am I in the middle there? Yes. And then what was the next one after 11? 14. Am I at the minimum of negative 12? And then one more, 15, 16, 17. And there it is, negative 5 again. See? Cool, right? All right, let's keep going. Don't worry, guys. We only got 2 left, and then these are actually easier. At least the other class found these easier. So you have a graph, and now you're just finding the equation. That's all you're doing. So this one, it's easier to do it with cosine because we have a peak that they identified. In a little bit, we'll do on with sine. So first, write out cosine. Y equals a cosine b x minus c close plus d. Just go down the alphabet. I know that the midline is in the middle between the highest and the lowest. How do you find middle of anything? Divide by 2. Divide by 2. So we're going to go, here we go, guys. We're going to go, the midline is nothing more than the max, 56, plus the minimum, negative 38. And we're going to divide that sucker by 2. And that's going to give you my midline. Let's see, 38, 48, 58, that's 18, divided by 2, 9. Do you see how we got it, guys? So that's my midline. So let me see what the scale is on this. 10, 20, 30, 40, 50. It's looking like it's going by 10. So the midline is like right below that 10 there, just barely. Are we still cool? All right, I can find the amplitude. The amplitude is the distance from the highest point to my midline. Ooh, maybe that's one I didn't cover, but we figured it out earlier. The amplitude is the distance from the highest point to the midline. You could also say the magnitude from the lowest point to the midline. It's the same, but absolute value. So 56 minus 9, what's that? 47. And that's it. 47, guys. That's your amplitude. Do you see how we got it? Okay. D is the midline, yes. And A is the amplitude. So we got A and we got D, so now we need to get C. So what's my shift of the peak? Yeah, 3 to the right. Good job. So C is just 3. I'm going to write 3 to the right. 3 to the right. And in parentheses put for cosine. Because we're looking specifically at cosine. And the last thing I need is the b. So we're going to find the b by finding the period here. So if I have a peak at 3 and then I have another peak at 23. So let's see, 360 divided by period. And then on the side I'm going to write period is equal to 23 minus 3, which is 20. And it's a degree, but that's fine if you forget it. 360 divided by 20. I don't know if that reduces. Well, wait, it does. 2 goes into 36. What's that? 20, 18? So 18 times. So there it is, guys. We got everything. So the equation is y equals 47 cosine, open parenthesis. What was the b? 18, open, x minus 3, close, plus 9. And I would put check work somewhere, like check by graphing. You guys want me to check it really fast? All right, let's check it. Hook me up. What was the equation?
Y equals 47 cosine, parentheses 18, parentheses x minus 3, close,
Plus 9. Let's see. Window. I already forgot. Where did I go to? What's the lowest? Negative 38. So I'm going to... Oh, actually, negative... Okay, I got it. Negative 5 to 45, that's fine. And then negative 45 to 70. So we can add some space. X by 10. Graph. There it is, guys. Let's check it. Let's put some points. Trace. What point did they give me? 3. Enter. And there it is, 356. What was the low point? Give me the x coordinate. What was it? 13. 13, enter, and check it out. There it is, negative 38. And then give me one more high point. What was the other one? 20 something? 23, enter. And there it is, guys. It works. Cool, right? All right. Last one. And this is how y'all's assignment's going to look, like this. And you can work in groups, so it's all good. The figure below shows a quarter cycle. What does a quarter cycle mean?
1/4.
Yeah, 1/4, 25% of a cycle. Don't worry, guys. There's the last one. Write a particular equation and check it by plotting it on your graphing calculator. All right. Because this is 25%, does this look like a low to you? Yeah. So then that must be a point of inflection. The 8. So the 8 is the midline. So from there, I can tell what my amplitude is going to be. The difference between 8 and 3 is 5. So I'm going to go 5 up. It's going to be like somewhere up here. 8, 9, 10, 11, 12, 13. So I'll put the number 13. So from point of inflection, let's see. Before I do that, let me see what the difference is between 17 and 24. The difference between 17 and 24 is 7 degrees. So I'm going to go another 7 degrees. So let me see if I can make it symmetric. I'm going to go to the left first. So there it is, 7 degrees to the left. And that's a peak. So I can use cosine if I want, but I don't want to. Let me go. Well, I'm going to use both just in case. I'm going to go another 7 to the left, so it looks like 3 there. Point of inflection going up. All right. I think that's well. No, let's do some more. 20. Now I'm at 24. I'm going to go 7 to the right. So what's that? 31. 31 degrees. Point of inflection, and there. I have enough. I have a whole cycle. Chavez, what do you mean I have a whole cycle? I have this guy and this guy. That's a point of inflection going up to a point of inflection going up. So that's one cycle there. Do you guys see that? All right, here we go. Let's answer the question. Let's do, since we probably think cosine's easier because we've just done back-to-back problems with cosine. So let's do cosine first. A cosine B, x minus c, close, plus d. What's the amplitude? 5. How'd you get it? Yeah, 13 minus 8 or 8 minus 3, it doesn't matter. So there it is. Amplitude is 5. If I use cosine, what is my horizontal shift? Or phase displacement? Look at the peak. No, look at the peak. No, not 3. 10. To the right. For cosine. We still okay? What is my midline? D. 8. I heard someone say it. And the only thing I got left to calculate is the B. B is calculated by doing 360 divided by the period. The period is not 7 degrees. So I'm going to come over here to the side. No, it's not 14 either. 7 times 4. Or you can say 3 and 31, the difference between that, right? 7 times 4 is 28. Do we know how we got 28?
No.
Okay. 7 degrees is my period for a quarter of a cycle. So 7 times 4 will give me the whole cycle, which is the period. One cycle is a period. Right?
Oh.
Do you know what I mean or no? See? The period, there's one cycle there. So one cycle is the period. You could also have done this, guys, from the green to the green. Notice point of inflection there. So 3 degrees, point of inflection going up. 31 degrees, there's one complete cycle. 31 minus 3 is also 28 degrees. Cool?
Yes.
All right, 360 divided by 28. I do not think that reduces. Let's see. Second quit. 360 divided by 28. Enter, math, fraction, enter. Nope. Leave it as 90 over 7. 90 over 7. So here's my equation for in terms of cosine. So y equals 5 cosine, open parenthesis, 90 over 7, open again, x minus 10 degrees, close, close. If you forget the degree symbol, no big deal. Plus 8. Now catch up, and then we'll talk about how it would look in terms of sine. It's going to be simple, guys, don't worry. All right. Don't worry, Villanueva, we're almost done. Wake up. Let's put some hype music. Turn down. Oh, I'll stop. No, we're good. All right, here we go. Ready, guys? What if I wanted this in sine? What if I wanted, so I'm going to write the sine formula. All I'm doing is replacing cosine with sine, literally. A sine B x minus c, close, close, plus d. You can express any sine. This is a wave, and sine and cosine look exactly the same. So that means sine is going to have the same amplitude, the same b, the same d. The only thing that changes is your c. So Chavez, what is the c? All right, let's observe real quick. Go back to your notes, or you don't have to go back. Just look up here, go real quick. So notice, what do you notice about sine? Where did it start? Notice it's point of inflection on the way up, because there's another one, right? This is another point of inflection, but on the way down. So we always read a graph left to right. Notice I started a point of inflection on the way up. So let's go back over here, and I'm going to look. There's two choices that I can use, and they will both give me the same answer. I'm looking for a point of inflection on the way up. Which one am I going to use? You can use either one. What number? What's my x-coordinate? 3. There it is. This one. You could also use 31, and it will give you the same thing. So here we go, guys. And don't worry. You know what? I might even put both of them right now in a little bit. So y equals 5 sine, open parenthesis, 90 over 7, open, x minus 3 per degree, close, close, plus 8. And don't worry, we're going to put them in the graph so you can see that it's the same. So here it is. Let me put them in my equation, my calculator here. Y equals, hook me up again, guys. One last time. Give me the cosine first. 5 cosine 90 over 7 x minus 10 close, close, plus 8. Plus 8, right? Okay. And we're going to do the same thing. 5 sine 90 over 7 open x minus 3, close, close, plus 8. And let me see my window. My window, okay, 0 to 40, and got it. So window 0 to 40, that's fine. And then 0 to 15. So check it out. Look at that. They're both the same. Cool, right? Let's click trace really quick just to make sure. What values do I know for a fact? 3. Let's 3. Enter. Check it out. Y equals 8. If you want to see the midline, you're gonna have to literally just let's put that visual. Y equals 8 here. There it is. So now you can see the visual. Trace. 3. Enter. 3, 8. Cool, right? And then what was my high point at 10? 10. Enter. There it at 13. Cool. What was my low point? Give me 24. 24. Enter. Look at that, guys. It works. You guys did it. Good job. So that's why you guys are going to have fun with this. Turn up.
Turn down.
No. Turn down for what?